Project Lawful aka Planecrash by Arwayne aka Eliezer Yudkowsky and Lintamande. The Alien Maths of Dath Ilan, Episode 138.
This is a lecture episode, The Alien Maths of Dath Ilan, dealing with Laplace's rule of succession. It should be possible to abandon this episode and skip to the next one if necessary, without missing out on plot-critical developments. Warning: dubious infinitary mathematics. Peel timestamp, day 2420, morning lecture.
The rule of succession. This is sort of picking up the topic from last time about science. How to do statistical inference in cases slightly more complicated than the trivial ones discussed previously. Asmodia has now supposedly had the time to teach the new candidates some additional law of probability, aided by Meritzel. People have cast a few foxes' cunnings on themselves and others. They will now try again to see if that sufficed for old hands to teach new hands. Suppose Keltham takes a sphere, puts it on a table with bouncy boundaries, shoves it rolling quickly, and lets it bounce back and forth many times until it comes to a halt, somewhere random. Object Keltham should theoretically be considered as doing this in private, where the object. Others can't see him, though for illustration purposes, meta, Keltham will write down everything plainly for people's meta, selves in class. Object Keltham marks down where ball 0 landed, picks up the ball, and again rolls it hard. Object Keltham then asks the object, classroom for their odds that ball 1 landed to the left or the right of ball 0. Remember, their meta-selves can see where Keltham made the marks on the whiteboard representing where ball 0 and ball 1 landed, but their object selves can't. Before being told the answer, what probability should their object selves assign that ball 1 landed to the left or right of ball 0, after both balls bounced back and forth on the table many times? Their object selves know the experimental setup. They just don't know the detailed results until object Keltham tells them.
Seems like they should assign a 50% chance, because the situation is symmetrical. From the information they have, there's no reason to expect ball 1 to be more left or more right than ball 0.
Object Keltham tells the object class that ball 1 was indeed to the right of wherever ball 0 landed. They know nothing else about where ball 1 or ball 0 landed, as yet, just that ball 1 was to the right of ball 0. Object class only knows 1, right. Ball 2 is now rolled, same setup. What probability do they assign that ball 2 falls to the left or right of ball 0?
Okay, I see why it's not just 50% now, because our guess about where the first ball lands shifts when we learn the second ball landed to the right of it. It's the same as spinning a coin, where the ball 0 is like deciding if the coin is weighted. And then the subsequent spins give you information about how weighted and in which direction.
Indeed, the object class can now be quite confident that ball 0 did not stop exactly up against the right wall, in which case the chance of ball 1 landing further to the right would have been 0. Surely they have no more information than this, however.
No, they have more information than that. Like, it's also less likely the ball is very near the right wall. It's just not immediately obvious how to plug it into the formulas from last class. If there were just 3 positions it could be in, you've ruled out it being at the right end, and if it was in the middle, ball 1 result was 50-50. If it was on the left end, ball 1 result was certain. So, in that example, we should guess it's at the left end twice as often, so 2/3 versus 1/3. So then 2/3 times 2/3 ball, 2 is to the right, plus 1/3 times 1/3 ball, 2 is to the right. So 5/9.
I think I see what you were trying to do there, but I don't think the numbers work out. Ball 0 could be all the way on the left, in the middle, or on the right. The new chance that it's all the way on the right is 0, and if ball 0 was in the middle, we're half as likely to hear right than if ball 0 was all the way on the left. So the new chances are 2/3 that ball 0 was all the way on the left, times a probability of 1 of hearing right then, plus a 1/3 chance that ball 0 was in the middle, times a 1/2 probability of hearing right then. 2/3 times 1 plus 1/3 times 1/2 equals 5/6 chance of hearing right next time.
If, however, we actually look at what Metakeltham drew on the wall, it seems like a pretty reasonable way things could be, and in that way things could be, we're not supposed to say 5, 6. I mean, think about it. If this actually happened, and Keltham said, right one time, would you immediately afterwards go, well, I guess the chance of hearing right next time is 5, 6. Hearing right one time shouldn't actually make you that confident about it happening again.
It's still information, though. In all of the situations where ball 0 is left of center, ball 1 was more than 50% likely to be right of it, and in all of the situations where ball 0 is right of center, ball 1 is less than 50% likely to be right of it. So the fact that it's to the right is some update towards ball 0 being left of center, which suggests that ball 2 is also more likely to be to the right of ball 0, but I don't know how you'd tell what the numbers are.
Let's say we divide it into 11 possible positions. If ball 0 arrives all the way on the right, chances of hearing right are 0 out of 10. If ball 0 is 90% of the way to the right, chances of hearing right are 1 out of 10. So it's 1/10 squared plus 2/10 squared plus 3/10 squared, which is 1 plus 4 plus 9 plus 16. I get 285 over 100. What did I do wrong?
Forget to multiply each of those terms by their 1/11th prior probability.
285 over 1100 chance of hearing right next time.
Pretty sure we should expect to hear right more than we expect to hear left.
Let us possibly try this with 5 positions before going straight to 10. 0 out of 4, 1/4, 2/4, 3/4, 4/4 likelihood of yielding right. All positions equally probable before then. We see 1 right. The likelihoods are 0 out of 4, 1/4, 2/4, 3/4, 4/4. The posteriors are, I see the other 2 things Pilar did wrong. We start with 5 hypotheses, 0 out of 4, 1/4, 2/4, 3/4, 4/4, each of which has prior probability 1/5. After seeing right one time, we've got priors times likelihoods of 0 out of 20, 1/20, 2/20, 3/20, 4/20. The relative odds of the posterior will be proportional to the priors times likelihoods, but they have to sum to 1. There's 1 plus 2 plus 3 plus 4 equals 10 total shares of 20ths, but it doesn't matter what exactly. So the posterior distribution is 0, 1/10, 2/10, 3/10, 4/10, summing to 1. Then if you take the likelihoods off each of those, weighted by the new posterior probability, you get 1 plus 4 plus 9 plus 16 divided by 40 equals 3/4.
Keltham will helpfully write down the calculation as Modia actually did. There, 0 out of 10 times 0 plus 1/10 times 1/4 plus 2/10 times 2/4 plus 3/10 times 3/4 plus 4/10 times 1 equals 1/40 plus 4/40 plus 9/40 plus 16/40 equals 30/40.
With 7 positions, it's 0 plus 1 plus 4 plus 9 plus 16 plus 25 plus 36 divided by 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 times 6, so 91 over 126.
Well, how about infinity positions then?
Are you in fact allowed to just do that?
Well, I don't see who's going to arrest you if you just try.
All right then. I get 1 squared plus 2 squared plus 3 squared out to infinity divided by 1 plus 2 plus 3 out to infinity times infinity.
Great. Now simplify that expression.
One of the older students in the background does happen to know the useful fact that summing from 1 to n gives you n times n plus 1 over 2, and summing the squares from 1 to n gives you n times n plus 1 times 2, n plus 1 over 6. Somebody asks if summing 1 to n gives n times n plus 1 over 2, and summing squares gives n times n plus 1 times 2, n plus 1 over 6 are to be treated as brute facts or the sort of things you can prove.
Keltham is not usually one to duck into details that aren't relative to the main line of argument, but this question is sort of alarming. Keltham will observe that 1 plus 2 plus 3 plus 4 plus 5 plus 6 equals 1 plus 6, plus 2 plus 5 plus 3 plus 4 equals 7 plus 7 plus 7, and that 1 plus 2 plus 3 plus 4 plus 5 equals 1 plus 5 plus 2 plus 4 plus 3 equals 6 plus 6 plus 6 over 2. Proof by generalizing examples. Sum of 1 plus 2 plus n with n terms equals half that many n plus 1 terms, so n over 2 times n plus 1 equals n times n plus 1 over 2. Keltham doesn't really want to stop and prove. The sum of n squared from 1 to n is n times n plus 1 times 2, n plus 1 over 6, using properly hasty, intuitive reasoning that will create a good sense for what's really going on. So instead, he'll just quickly write on the board that let f of n equals n times n plus 1 times 2, n plus 1 over 6, in f of 0 equals 0 f of n plus 1 equals f of n plus 1 squared proof. 0 times 0 plus 1 times 2 times 0 plus 1 equals 0 times 1 times 3 equals 0 f of n plus 1 minus f of n equals n plus 1 times n plus 1 plus 1 times 2 times n plus 1 over 6 minus n times n plus 1 times 2 n plus 1 over 6 equals n plus 1 times n plus 2 times 2, n plus 3 over 6 minus n times n plus 1 times 2, n plus 1 over 6 equals n plus 1 times n plus 2 times 2, n plus 3 minus n times 2, n plus 1 over 6 equals n plus 1 times 2, n squared plus 7, n plus 6 minus 2, n squared minus n over 6 equals n plus 1 times 6, n plus 6 over 6 equals n plus 1 squared. If they're not happy with this logical proof by certain reasoning, because, why? They should consider visualizing stacking a bunch of n-sided squares on top of each other to form a figure that pretty much looks like it should take up about a third of a cube of size n. Now, back to the problem of evaluating 1 squared plus 2 squared plus 3 squared plus 4 squared plus divided by 1 plus 2 plus 3 plus 4 plus times infinity.
Then Pilar will obtain the sum n times n plus 1 times 2, n plus 1 over 6, divided by n times n plus 1 over 2. Letting n equals infinity, this yields infinity times infinity plus 1 times 2, infinity plus 1 over 6, divided by infinity times infinity plus 1 over 2. Simplifying produces 2 infinity plus 1 over infinity times 3. This then cannot be simplified further.
Why? Of course it can be. Keltham writes on the wall, 2 times infinity plus 1, 2 times infinity, 1 infinity times 3, infinity times 3, infinity times 3. 1 divided by 3 infinities simplifies to 0, obviously. Think of how little cake each person gets if you divide one slice of cake among all the billion people in Galarian. 1/3 divided by infinity is much less than that. So this whole expression simplifies to 2/3.
Is that actually lawful reasoning?
It's lawful when he does it, in a way that carefully doesn't take any mathematical reasoning steps that would actually be invalid. Keltham would not necessarily advise Pilar trying this on her own for a little while, or rather, she should try it, but be prepared to fail. Pilar may, for her own reassurance, note that her previous answer of 91 over 126 is not too far from 90 over 135, also known as 2 over 3.
Can't you just think of this as permutations of 3 things?
Can you?
There are 3 permutations which have 0 before 1. 0, 1, 2, 0, 2, 1, 2, 0, 1. Of these, 1/3 have 2 left of 0, and 2/3 have 2 right of 0.
So what you're saying here is that any of the possibilities are equally probable. I'm not sure how reasonable that is. It looks to me like the middle stretch is wider than the 2 ends.
We don't know that. In the object-level classroom.
So what you're saying here is that if I roll 3 balls back and forth, and they bounce back and forth a lot, they're equally likely to land in any of the 6 possible orders, so far as you know. Can that really be true? After all, there could be bumps in the table. The bouncy walls might not be perfect. I might have rolled the balls harder on some occasions than others.
If we don't know any of that on the object level, then, so far as we know, all 6 permutations are equally likely. You could say that sort of thing about any problem with permutations in it.
Oh, I suppose. Just don't forget, in real life, always cheat the shit out of anything if you can get any extra information like that. After all, if you think otherwise, why, that's the sort of thinking that might lead to you always insisting that all of the chemical elements were equally likely to be in any order on the periodic table, anytime you don't know for sure what order they have. So, how about if I then tell you that ball 2 landed to the right of ball 0? Again? What's the probability of right next time, with the third ball?
3/4, says the same person who asked about permutations last time. They've unfortunately written their name tag in letters too small to see from where Keltham is standing.
This one comes up left, though. Your prediction failed. All your theories were probably wrong.
No. We just ran into a 1/4 chance. That happens sometimes. Like with the chance of failure on an augury.
I suppose. We should just discard the evidence, then, since it's only to be expected that reality gives us the wrong result sometimes. You predict 3/4 right again next time?
You can, in fact, get 10-foot range on prestidigitation, though not when you're a wizard as fresh as Keltham. One of the students nearest that wall makes their own change to it without leaving their desk. 3/5 right, 2/5 left, they declare.
What if the 2 ball actually landed to the left of the 1 ball? They're not told which of those was true.
If those two possibilities are equally probable, then they can sum the probabilities, right? 1/2 chance of 3/5 plus 1/2 chance of 3/5 equals 3/5. You don't need to label them. That's 5 landing regions, 2 to the left and 3 to the right.
Does anyone want to object to the invalidity of that reasoning? Or alternatively, state a general rule for what to predict on the next round if you previously got n balls left and m balls right of the 0 ball, and that's all you know?
If you have n balls left, there are n+1 landing regions left, and m balls right gives m+1 landing regions right. So my first thought is n+1 over m+1.
Ah, yes. So if they have seen 1 ball go left and 0 balls go right, the chance of seeing it go left on the next round is 1 + 1 over 0 + 1 equals 2. So the probability of seeing left next time is 2. That sounds pretty reasonable to Keltham, though clearly anthropics were involved at some point. Maybe the balls are duplicating people once they start to go left.
They obviously meant, like, a ratio of n+1 to m+1, not to calculate the probability that way.
So, like, after seeing 1 ball go right, the chance of seeing it go left on the next round is half the chance of seeing it go right. That's what the n+1 over m+1 quantity is. How many times more likely left is than right? In this case, 0 + 1 over 1 + 1 equals 1/2. But how do they square that up with the previous claim as proven by dubious infinitary mathematics that, after seeing 1 right, the chance of the next ball landing right is 2/3?
It's the same claim. 1/3 left is half of 2/3 right.
But is it really?
Yes. Somebody would in fact now like to make the general claim that if n balls go left and m balls go right, the chances of the next ball landing left and right respectively are n+1 over n plus m plus 2 versus m+1 over n plus m plus 2.
Keltham agrees. Now, would anybody like to try to prove that claim using dubious infinitary mathematics?
I'd love to, but I don't know where to start. Well, actually, I guess the obvious place would be with 2 right and 1 left, and seeing if we can make that come out to 2 5 left and 3 5 right, and then seeing if we can get it to generalize.
Several of the new students do in fact know calculus, and that seems like the obvious tool to use on this problem.
Ah, yes, Galarian's notion of calculus. Keltham has actually looked into it now. It looked like one of several boring, safe versions of dubious infinitary mathematics, where you do all the reasoning steps more slowly, and they only give you correct answers. Dath Ilani children eventually get prompted into inventing versions like that, after they've had a few years of fun taking leaps onto shaky ground and learning which steps land well. Those few years of fun are important. They teach you an intuitive sense of which quick, short reasoning steps people can get away with. It prevents you from learning bad habits about reasoning slowly and carefully all the time, even when that's less enjoyable, or starting to think that rigor is necessary to get the correct answer in mathematics.
Pilar has not yet been exposed to professional Galarian mathematicians talking about the importance of rigor. It will probably be a powerful theological experience for her when she does. Meanwhile, she already has a strong sense that Keltham needs to be burned as a heretic. Don't I need to reason correctly to arrive at correct answers?
I don't think we have several years to spend on free-form mathematical exploration, even if we should make it an educational priority for the next generation.
Rigor is necessary to know you got the correct answers. Non-rigorous reasoning still often gets you correct answers. You just don't know that they're correct. The map is not the territory. Often, though not literally always, the obvious methodology in mathematics is to first rapid prototype an answer using non-rigorous reasoning. And then, once you have a strong guess about where you're going, what you're trying to prove, you prove it more rigorously. We don't have years to spend doing all of our mathematical reasoning rigorously the first time around, and besides, who does that anyways? And also, I'm here and can potentially check whether your fast, crazy reasoning steps were valid or not.
Somebody is currently trying to solve the case for 1 left, 2 right, by visualizing how you'd carve off pieces of a 5-dimensional hypercube. No, actually, just a 4-dimensional hypercube. This is apparently the sort of thing you learn in math class as a relatively advanced wizard, though you don't need it to hang most second circle spells. Their first attempt to simplify down to 0 left, 1 right, and a 2-dimensional triangle doesn't end well for them, though. Other researcher candidates seem to mostly be trying to rework Pilar and Asmodea's original workings with the 5 possible positions and the 7 possible positions. Never mind the dubious infinitary mathematics after that.
Okay, Asmodea's just going to try this thing with the dubious infinitary mathematics. If not her, then who? Asmodea alone is protected from any vengeance the afterlife might visit on her. Consider the case for 1 left and 2 right first. They start with an infinite number of points between 0 and 1 probability of yielding left, each with prior probability 1 over infinity. For each of those points, p on the spectrum from 0 to 1, their likelihood of yielding 1 left and 2 right is p to the power of 1 times 1 minus p to the power of 2 equals p minus 2p to the power of 2 plus p to the power of 3. Then, to get the posterior, Asmodea has to. Well, to be honest, she has in fact tried to get calculus off some securities, and she is having to exert something of a deliberate effort not to use that. But the calculus also wasn't. The thing that she can feel Keltham is trying to teach? Asmodea is getting a sense of the way that Keltham teaches intuitions and not just formulas. She thinks it's meant to teach the thing that Ione does a little better than Asmodea. A little better. Asmodea wants to learn it. The way they got here before was by Pilar trying it with 5 exact hypotheses for p, then 7 hypotheses for p, then an infinite number of hypotheses for p. Let's say there were 4 hypotheses, 0 over 3, 1 over 3, 2 over 3, 3 over 3, probability of left, and you saw 1 left and 2 right. Then you would sum up 1/4 times 0 plus 1, 4th times 1 over 3 to the power of 1 times 2 over 3 to the power of 2 plus 1, 4th times 2 over 3 to the power of 1 times 1 over 3 to the power of 2 plus 1, 4th times 0. That would give you the posterior distribution of, some stuff just cancels out there actually, 1 to the power of 1 times 2 to the power of 2 plus 2 to the power of 1 times 1 to the power of 2, and then, after dividing through by that, actually, a lot of this stuff is going to cancel out anyways, isn't it? But finish the calculation anyways. After that, we get the 1 over 3 hypothesis with posterior probability 4 over 4 plus 2, and the 2 over 3 hypothesis with posterior 2 over 4 plus 2. Then, to get the prediction of left next time, it's 2 over 3, probability on the 1 over 3 hypothesis, which contributes 2 over 9 to left, and 1 over 3, probability on the 2 over 3 hypothesis, which contributes 2 over 9 to left, and it comes out as 4 over 9 total prediction for left, which does at least match that they originally saw more right than left. Now do the infinitary version.
Meanwhile, one of the newer researchers has worked out that, in the earlier formula, 0 over 10 times 0 plus 1 over 10 times 1 over 4 plus 2 over 10 times 2 over 4 plus 3 over 10 times 3 over 4 plus 4 over 10 times 1. That first term, 0 over 10 times 0, has the 0 over 10 subterm representing the probability that the fraction of rights is 0, given that the first ball landed right, and the 0 subterm representing the probability that ball 2 lands right, given that the fraction of rights is 0.
Okay, yeah. If she's not just allowed to throw calculus at it, or take limits in a way that just rederives Galarian-style calculus, Asmodia isn't really seeing how the Dath Ilan dubious infinitary reasoning version works.
Ione already knows the answer is n plus 1 divided by n plus m plus 2 via a perfectly valid combinatorics argument. She shouldn't have to rigorously prove things when she already knows the correct answer, or even prove them using dubious infinitary arguments. This is Nethisian abuse. Aren't only Asmodeans supposed to treat people like this? She's sure it's not how Nethisian math classes work.
Keltham starts by considering the case where n balls go left and 0 balls go right. Then every point lying a fraction p along the way from the left side to the right side has a likelihood p to the power of n of yielding the data we saw.
One student is having some trouble parsing this, despite Keltham's gainful attempts to speak slowly. The p is a position along a line from 0 to 1, and the p to the power of n is, if the 0 ball landed at that point, how likely it is that it yielded the data we saw. But p equals 0 at the far left. Shouldn't it be infinitely likely it be to the left of the furthest left point, instead of no chance whatsoever? A moment later, they've worked out that no, the next ball has probability 0 of being any further left than as far left as possible, and the whole thing flips around in their head.
But by then, of course, Keltham has already continued talking. The prior probability is the same everywhere, so the posterior function will be proportional to p to the power of n everywhere. If you wanted the whole thing to sum to 1, you'd divide every point by whatever p to the power of n sums to between 0 and 1.
Excuse me. Alexander raises his hand, since showing weakness in this environment appears to be less bad than possessing it. Divide every point by whatever p to the power of n sums to between 0 and 1. Can I ask you to expand on that?
Keltham shall be happy to do so. Thank you for providing any feedback on where anyone is getting lost. As a simple example, take the case of n equals 1. So p to the power of n equals p. If you graph that, you get a straight line from likelihood equals 0 at p equals 0 to likelihood 1 at p equals 1. That graph looks like a triangle filling half of a square with side 1. So by visual reasoning, the sum 1 divided by infinity times 0 divided by infinity plus 1 divided by infinity plus 2 divided by infinity plus infinity divided by infinity equals 1/2 in the end. Proof by dubious infinitary mathematics, now that they know the correct answer by simpler visual reasoning. 1 plus 2 plus infinity equals infinity times infinity plus 1 divided by 2. 1 divided by infinity times 0 divided by infinity plus 1 divided by infinity plus 2 divided by infinity plus infinity divided by infinity. 1 divided by infinity times 1 divided by infinity times 1 plus 2 plus infinity. 1 divided by infinity times 1 divided by infinity times infinity plus 1 divided by 2. Infinity times infinity plus 1 divided by infinity times 2. 1/2. Then to find a probability distribution proportional to that prior times likelihood object, but which sums to 1 to form the posterior, they divide the whole thing by 1/2 or multiply it by 2. 1 divided by infinity times 0 divided by infinity plus 1 divided by infinity plus infinity divided by infinity divided by 1/2 equals 1. As Keltham is saying this, it occurs to him that it may not be obvious to the candidates why you'd do that, depending on what got covered in previous probability classes and how well. He'll expand on that too. If they were just tracking, say, 1/2 prior probability of propensity, 1/3 versus 1/2 prior probability of propensity 2/3, the prior times likelihood object would look like set of 1/2 times 1/3, 1/2 times 2/3, and the sum over the prior times likelihood object would look like set of 1/6 plus 1/3 equals 1/2, which is just what it should be. Because if you start with 50-50 on 1/3 versus 2/3, then your prior probability of seeing the ball go left is indeed 1/2. Conversely, the prior time likelihood object for seeing right is set of 1/2 times 1 minus 1/3, 1/2 times 1 minus 2/3 equals set of 1/2 times 2/3, 1/2 times 1/3 equals set of 1/3, 1/6, again summing to 1/2. This should look like it makes lots of sense. On priors, you think either the ball goes left or the ball goes right, but not both, nor neither, so your prior probability of left plus your probability of right should sum to 1. But after actually seeing the ball go left and updating on that, you throw out all the possible worlds from your probability distribution where the ball went right, and live only inside the worlds where the ball went left. After seeing left, then, within this kind of hypothesis, where you're not questioning the whole setup from outside, you're certain that the ball went left. It's now probability 1 that the ball went left. The probability 1 of what is real is divided up among the surviving worlds. The surviving worlds should have probability proportional to their prior times, their likelihood, but summing to 1. So you divide through a set of 1/6, 1/3, by its total probability of 1/2 to get set of 1/3, 2/3 as the posterior probability. In symbolic terms, there's probability of propensity. 1/3 equals 50%. Probability of propensity. 2/3 equals 50%. Probability of true equals probability of propensity 1/3 plus. Probability of propensity 2/3 equals 1. Probability of left given propensity 1/3 equals 1/3. Probability of left equals probability of left and propensity 1/3 plus. Probability of left and propensity 2/3 equals probability of left given propensity 1/3 times. Probability of propensity 1/3 plus probability of left given propensity 2/3 times. Probability of propensity 2/3 equals 1/3 times 50% plus 2/3 times 50% equals 1/2. Probability of propensity 1/3 given left equals probability of propensity 1/3 and left divided by probability of left equals 1/6 divided by 1/2 equals 1/3. Probability of propensity 1/3 given left plus probability of propensity 2/3 given left equals probability of true equals 1. So to get the posterior probability on all the hypotheses between 0 and 1, after seeing n balls go left, they take the prior times likelihood object, which is 1 divided by infinity, times 0 divided by infinity to the power of n plus 1 divided by infinity to the power of n plus infinity divided by infinity to the power of n, and divide it through by its sum, so that the probability inside the whole thing sums to 1. If we started out certain that the ball has a propensity between 0 and 1 to go left or right, and then we observe n lefts, we end up still certain that the ball has some propensity between 0 and 1 to go left. So the question then becomes 1 divided by infinity times 0 divided by infinity to the power of n plus 1 divided by infinity to the power of n plus infinity divided by infinity to the power of n equals what? Now, before they try to prove a correct answer, they should, of course, first figure out what the correct answer is, so they can prove it. The correct answer in this case obviously has to be that it sums to 1 divided by n plus 1. Why? Well, you saw n balls go left. On the first round, that had probability 1/2. On the second round, you thought there was a 2/3 chance of seeing left, and then you saw it, so your joint probability over all predictions is now 1/2 times 2/3 equals 1/3, after seeing 2 left. On the third round, you think there's a 3/4 chance of seeing left, so your joint probability goes to 1/2 times 2/3 times 3/4 equals 1/4 after seeing 3 left. Since your joint probability of seeing n balls go left is 1 divided by n plus 1, the sum from 0 to 1 of an infinite number of points each with weight p to the power of n for how much they predicted seeing n balls going left must clearly end up as 1 divided by n plus 1.
Pilar is feeling, on some deep instinctive level, that her soul may be in danger here. This is not how math works.
It's fine. They derive that the final answer has to be 1/n plus 1 from combinatoric reasoning about the probability, which is simple and reliable, so they now know that's where any dubious infinitary reasoning about the same probability ought to end up. The problem before them, then, is to sum up. The limit as infinity approaches of 1 divided by infinity times the sum from 0 to infinity of the fraction 0 divided by infinity raised to the power of n plus the fraction 1 divided by infinity raised to the power of n plus the fraction 2 divided by infinity raised to the power of n, and so on until the fraction infinity divided by infinity raised to the power of n. To be clear on what this is intended to mean, the terms 0 divided by infinity, 1 divided by infinity, 2 divided by infinity up to infinity, divided by infinity are an infinite number of distinct hypotheses covering the spectrum from 0 to 1 of left frequencies. Raising a hypothesis for a frequency between 0 and 1 to the power of n gives that hypothesis's likelihood for generating the observed data of n lefts, and the 1 divided by infinity term at the start is being factored out from every hypothesis in the sum having 1 divided by infinity prior probability, where, again, the answer must be 1 divided by n plus 1.
Am I getting it right that the contribution from 2 divided by infinity raised to the power of n is obviously just 0?
Obviously. If you pick any finite number, you're starting infinitely close to a 0 probability of generating any lefts. It's only once you start getting a finite fraction of the way towards infinity that dividing by infinity won't just yield 0 again, intuitively speaking. Don't worry, only 0% of the numbers between 0 and INF are finite, so it makes sense that they'd contribute 0% of the likelihood.
Well, if I had any doubt before that you came from some plane of existence completely alien to Galarian, it's gone now. This is not how Galarian mathematics works.
Ilan has many different ways of looking at ideas like the integers or the points between 0 and 1, and teaches its children to switch between them as appropriate, especially when they are doing rapidly prototyped mathematics.
The problem before them is to sum up 0 divided by infinity raised to the power of n, 1 divided by infinity raised to the power of n, 2 divided by infinity raised to the power of n, infinity divided by infinity raised to the power of n, infinity, and get the correct answer of 1 divided by n plus 1. This obviously reduces to summing 0 divided by infinity raised to the power of n plus 1 divided by infinity raised to the power of n plus 2 divided by infinity raised to the power of n plus infinity divided by infinity raised to the power of n, and getting infinity divided by n plus 1.
So, a hand goes up. It is the hand of a student who does not want to admit weakness, but will do so anyway, under the eyes of security. It isn't obvious to me how that reduces.
Keltham starts to answer.
Oh wait, never mind, it is obvious.
It's too late to say that now, though, so the student will just listen to Keltham speak the awful words that he's just multiplying both the original sum and the original result 1, divided by n plus 1 by infinity. Factoring out 1 divided by infinity, raised to the power of n, from all the terms n divided by infinity, raised to the power of n reduces the problem to one of summing. 0 raised to the power of n plus 1, raised to the power of n plus 2, raised to the power of n plus 3, raised to the power of n plus infinity raised to the power of n. And getting infinity raised to the power of n plus 1 divided by n plus 1.
A hand goes up, in obedience to stated orders. Why are we factoring this out, sir? And why does it require summing this?
They're taking 0 divided by infinity, raised to the power of n plus, and factoring out 1 divided by infinity, raised to the power of n from all terms, n divided by infinity raised to the power of n to yield n raised to the power of n times 1 divided by infinity raised to the power of n for each term, and then dividing both sides to yield the sum over n raised to the power of n equaling infinity, divided by n plus 1, divided by 1, divided by infinity, raised to the power of n equals infinity. Raised to the power of n plus 1 divided by n plus 1. Then, once they get the solution for an infinite sum of cubes, n raised to the power of n, they'll multiply that whole thing through by 1, divided by infinity raised to the power of n, and by 1 divided by infinity, and get back out. 0 divided by infinity raised to the power of n, 1 divided by infinity raised to the power of n, 2 divided by infinity raised to the power of n, infinity divided by infinity raised to the power of n. Infinity, 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 which represents an infinity of possible hypotheses for all possible propensities between 0 and 1 for how often a ball goes left. Each hypothesis with 1 divided by infinity prior probability. Look, it's just the same as if they'd used 4 buckets each, with 1 divided by 4 prior probability, and asked for the chance of seeing 9 balls going left. That would be 0 divided by 3, raised to the power of 9. 1 divided by 3 raised to the power of 9. 2 divided by 3 raised to the power of 9. 3 divided by 3 raised to the power of 9. Somebody then asks whether it ought to be infinity plus 1 in the denominator of the original expression. Keltham stares at the wall for a moment, then sagely announces that, with a sum this large, it won't make any relative difference if they drop any finite number of terms from it, since those contribute 0% of anything. He's just going to arbitrarily declare that one of the ones in the middle is missing. Now, in an intuitive sense, infinity raised to the power of n plus 1 divided by n plus 1 is obviously what the answer has to be, of course. If you stack up a bunch of one-dimensional lines of length 1, 2, 3, up to 10, you end up with roughly half of a two-dimensional square of side 10. If you stack up a bunch of two-dimensional squares each with sides 1, 2, 3, up to 10, you end up with roughly a third of a three-dimensional cube of side 10. So naturally, if you stack up a bunch of n-dimensional hypercubes with sides 1, 2, 3, up to infinity, you'll end up with exactly 1 divided by n plus 1 of an n plus 1-dimensional hypercube with side infinity.
This nerd snipes multiple researchers hard enough that they have trouble following the next few sentences, which, thankfully, aren't vital ones.
Actually, they might want to double-check that using numbers up to, say, 5 or so. 1 plus 2 plus 3 plus 4 plus 5 equals 15, which is not that far off from half of 25. 1 plus 4 plus 9 plus 16 plus 25 equals 55, which is not far off from 1/3 of 125. 1 plus 8 plus 27 plus 64 plus 125 equals 225, which is not far off from 1/4 of 625. The difference becomes a bit more noticeable each time, since there are extra terms in the sum beyond the one for side raised, to the power of n, plus 1 divided by n plus 1. But as you sum a larger number of terms, these extra terms grow less quickly, and can be ignored when the sums are infinite. Like 1 plus 2 plus 3 up to 100 equals 5,050, and that's pretty close to half of 10,000.
Someone is increasingly confused about how this infinity business works. Is infinity minus 1 a different number from infinity? Is infinity minus 2 plus 3 equal to 5?
Yes to both, obviously. The usual guideline for answering questions like that is to pretend that INF is a very large, finite number. The whole idea is that a bunch of things that are approximately true about large numbers become exactly true about INF.
How does that square with 2 divided by infinity being 0?
2 divided by a very large number is approximately 0, so 2 divided by infinity is exactly 0, so long as it isn't being multiplied by infinity somewhere outside that. Similarly, infinity minus 1 divided by infinity plus 1 equals infinity divided by infinity, which is 1.
Is there some precise sense of approximately that could be used to prove?
That sounds like a question slow people would ask. Boring question. Let's move on.
Keltham, has it ever occurred to you that, as an 8-year-old boy, You were taught mathematics in a style that someone thought would appeal to 8-year-old boys? She doesn't actually say it out loud, maybe when they're alone.
Now, the nice thing about working with infinities is that you don't have to be very precise at all, and you'll still get exactly the right answer at the end. Instead of taking x raised to the power of n, let's use rising powers. This didn't translate, so it's probably not a concept in Galarian, or at least the share language donor didn't know it. Instead of taking x multiplied by itself, n times, let's consider the expression x multiplied by x plus 1 multiplied by x plus 2 and so on until you've got n of those. Let's denote that as x rising to n. Obviously, if x is any finite fraction of the way towards infinity, x rising to n equals x raised to n exactly. Like, when you're working with trillions, a trillion squared is nearly the same number as a trillion times a trillion plus 1, proportionally speaking. With infinities, this becomes exactly true. Example with x equals 10 and n equals 3. X rising to n equals x multiplied by x plus 1 multiplied by x plus 2, so you end up with 10 multiplied by 11 multiplied by 12. This works with the general expression for x rising to n as well, which is x multiplied by x plus 1 all the way to x plus n minus 1. Now observe that. X plus 1 rising to n minus x rising to n equals n multiplied by x plus 1 rising to n minus 1. Rearrange x rising to n plus n multiplied by x plus 1 rising to n minus 1 equals x plus 1 rising to n. Here, we rephrase n as n plus 1 so that n minus 1 becomes n, simplifying the expression x rising to n plus 1 plus n plus 1 multiplied by x plus 1 rising to n equals x plus 1 rising to n plus 1. Sanity check with x equals 10 and n equals 2 passed. Then, by induction on ff of x equals x, rising to n plus 1. 0 rising to n plus 1 equals 0 as the base case. X plus 1 rising to n plus 1 equals x rising to n plus 1 plus n plus 1 multiplied by x plus 1 rising to n. Conclusion. The sum of 0 raised to n plus 1 raised to n plus 2 raised to n, and so on up to infinity, raised to n equals infinity, raised to n plus 1, divided by n plus 1. So if you stack up an infinite number of squares with sides 0, 1, 2, 3, and so on, you will get exactly a third of an infinitely large cube. More generally, if you stack up an infinite number of n-dimensional hypercubes with sides 0, 1, 2, 3, and so on, you'll get exactly 1 divided by n plus 1 of an infinite n plus one-dimensional hypercube. Which, in case anybody's forgotten by now, was what they needed to prove that. 1 divided by infinity multiplied by the sum of 0 divided by infinity raised to the power of n, plus 1 divided by infinity raised to the power of n, plus 2 divided by infinity raised to the power of n, and so on, up to infinity divided by infinity. Raised to the power of n is equal to 1 divided by n plus 1, which in turn is how you represent an infinite number of possible hypotheses about how far from 0% left to 100% left. The first ball 0 could have landed, each hypothesis with equal prior probability, 1 divided by infinity, and then update on seeing n balls go left, as would have a likelihood of p raised to the power of n for each hypothesis, a fraction p of the way between the left side and right side. Also, in case anybody's forgotten, if you imagine n balls plus the 0 ball getting randomly ordered, the chance of the 0 ball coming rightmost in the ordering, hence all other balls being left of it, is 1 divided by n plus 1, which is how they originally knew that 1 divided by n plus 1 was the desired end result, for the likelihood of seeing all n balls land on the left. Also, in case anybody's forgotten, the reason they needed this sum was to renormalize the relative probabilities into absolute probabilities. That's another step along the direct path to deriving a prediction about the next ball observed. After seeing n balls go left, the posterior distribution ends up proportional to a distribution where each hypothesis p has weight p, circumflex n. But if you forget to normalize that prior times likelihood distribution, and ask what happens if every part of the distribution then contributes pi, likelihood, to the next ball going left. You'd first add one extra factor of p everywhere, and then calculate 1 divided by infinity, multiplied by the sum of 0, divided by infinity, raised to the power of n plus 1 divided by infinity, raised to the power of n plus 1, and so on, up to infinity, divided by infinity raised to the power of n plus 1 is equal to 1 divided by n plus 2. After observing 100 balls go to the left, calculating a 1 in 102 chance for the next ball also going left is incorrect. You would actually expect the next ball to be more likely to go left. The mistake lies in the fact that we didn't normalize the prior times likelihood distribution. The pre-normalized distribution's total is 1 divided by n plus 1. To normalize it, the sum should be 1. So we divide every element by 1 over n plus 1, or equivalently, multiply by n plus 1 to make the distribution sum to 1. In this example, that means uniformly multiplying everything by 101 to normalize the distribution. This results in a 101 over 102 chance that the next ball will go left, which aligns better with expectations. Though, Keltham quickly remarks, the principle of making the posterior sum to 1 is something that only applies within that whole meta-hypothesis. If you see balls going left, right, repeating, you might form, after a few steps, the hypothesis that the ball goes left, right, repeating, which can't be expressed within that whole meta-hypothesis. All of this reasoning is taking place inside the meta-hypothesis about the balls having some stable but otherwise not further scrutable fractional propensity to go left or right, with all such propensities between 0 and 1 being equally likely on priors. This whole meta-hypothesis then may do better or worse compared to some other hypotheses. He's not saying that the meta-hypothesis absolutely has to be true, by saying that the sum of all the hypotheses inside it should be 1. If you started believing that, you'd never in principle be able to notice any other pattern, like left-right repeating. Rather, this whole meta-hypothesis is itself being entertained as one of many in-principle possible meta-hypotheses about how things could be, and the probabilities of all the hypotheses inside it summing to 1 are to be understood as being what we get when we entertain the possibility, condition on, reason inside, the meta-hypothesis being true. After seeing n balls go left, the whole meta-hypothesis has racked up a joint probability of 1 over n plus 1 and scored log of 1 over n plus 1 in terms of how well it's doing. If you previously started out with any prior credence on an incompatible meta-hypothesis, like actually maybe the ball just always goes left or right, both equally credible on priors, that other meta-hypothesis may be doing better. In fact, the always left or always right meta-hypothesis has now racked up probability 1/2 and a score of log of 1/2 equals -1, which is probably quite a bit better than 1 over n plus 1 if you've seen a lot of balls go left. You'd probably be believing in that meta-hypothesis a bit more. Now, even if it started out less meta-credible than the other.
Why do we need that other hypothesis, meta-hypothesis, about there being hypotheses where the ball always goes left or right? Aren't those hypotheses already inside the meta-hypothesis about all the fractions of times a ball could go left or right? Like 0 divided by infinity is that it never goes left, and infinity divided by infinity is that it always goes left. Am I missing something?
Both those hypotheses have prior probabilities of 1 INF, remember? That's equal to 0. So the meta-hypothesis thinks it's infinitely unlikely that the fraction of times the ball goes left is exactly equal to 1 or 0. It never notices that's true, no matter how many examples it sees. If it sees 100 balls go left, it'll get a joint prediction of 1/101. If it sees 10,000 balls go left, it'll get a joint prediction of 1/10,000 first. In the limit, the probability that it assigns to a sequence of left-going balls, continuing forever, is 0. Before you've rolled a single ball, the meta-hypothesis is already absolutely certain that it won't just go left every time. The alternative meta-hypothesis that the ball has a 50% chance of always going left and 50% chance of always going right loses all of its probability and scores negative infinity as soon as it sees any sequence with a mix of left and right balls. But if you present that meta-hypothesis with a sequence of balls going left forever, no matter how long that continues, it predicted that with 50% probability from the start. Keltham will now zoom in closer on what happens to the any fraction between 0 and 1 is equally likely meta-hypothesis when it updates. Let's say that we see 10 balls go left. After seeing 10 balls go left, the meta-hypothesis as a whole has a cumulative score of 1 divided by n plus 1 equals 1 divided by 11. Or equivalently, if you asked this meta-hypothesis at the dawn of time what probability it assigned to the first 10 balls going left, it would answer 1 divided by 11. Equivalently, isomorphically, these are stating the same thing. If you multiply out the prior distribution, 1 divided by infinity everywhere, and the likelihood distribution, p to the power of 10 everywhere, you'd get a new distribution p to the power of 10 divided by infinity, which, if you summed over the infinitely many terms inside it, would sum to 1 divided by 11. Continuing to reason within this meta-hypothesis, one of the internal sub-hypotheses must by assumption be true. And so within the meta-hypothesis, the posterior probabilities of the infinite collection of sub-hypotheses must sum to 1, which you'd obviously do by dividing all the terms through by 1 divided by 11, that is, multiplying them by 11. The distribution: 0 divided by infinity to the power of 10, 1 divided by infinity to the power of 10, infinity divided by infinity to the power of 10 infinity, times 1 divided by 11, infinity times 1 divided by 11, infinity times 1 divided by 11, will, indeed, sum to 1. To be clear, by having the distribution sum to 1, we are assuming for the sake of extrapolation that some hypothesis in the collection must be true. But no matter how far the posterior updates on finite data, every individual hypothesis in the collection will still have posterior 0. After rolling 1,000 balls and seeing 985 go left, there's finite probability between 0.98 and 0.99, but zero probability on the fraction being exactly 0.985. That's just how this meta-hypothesis rolls. If you wanted a meta-hypothesis that could put little finite dots of probability mass on all the big round numbers like 0.985, 1/2 pi, and so on, that would be a much more complicated ask. What we ask about, having updated, is not so much the probability of individual hypotheses, which is always 0, but the new shape of the curve. If you see 10 balls go left, the individual hypothesis 0.9 has now scored around 1e, 37% or so, compared to 1 to the individual hypothesis, 1.0. If you see 100 balls go left, raise all that to a power of 10. Now 0.9 will have less than 0.01%, the cumulative likelihood predicted as 1.0. On the scale of the curve, this means that over 99.99% of the probability is now concentrated into the interval between 90% and 100%, though of course still 0% is concentrated at exactly 100%. Keltham will prestidigitate sketch a few rough images of what curves like these should maybe probably look like, after updating on various numbers of left and right balls observed, keeping in mind that Keltham's not a computer and can't draw the curves perfectly.
One of the newcomers who does know what calculus is, and has indeed known it for years, asks a pending question he's had for a while. Are some of Keltham's earlier statements up until this point equivalent to, in Galarian notation, saying, integral of p from 0 to 1. The integral of p to the power of n with respect to p equals 1 divided by n plus 1.
Yes.
Lady Avaricia has gotten away with a lot around Keltham, and so has Ione. The newcomer will venture, very politely, that the calculus-based way of expressing this and calculating this seems to him simpler?
If you're willing to assume your audience can already freely wield the machinery of derivatives and antiderivatives and understand on an intuitive level everything that they mean, then sure, You can solve the problem more quickly using overpowered tools like that. Integrating x to the power of n gives you x to the power of n plus 1 divided by n plus 1, which evaluated from 0 to 1 will give you 1 divided by n plus 1. Given a mix of n lefts and m rights, however, and the need to renormalize the posterior over that, they might find themselves in a bit more trouble when it comes to deriving the integral. Integral of p from 0 to 1. The integral of 1 minus p to the power of m times p to the power of n with respect to p equals factorial of m times factorial of n divided by factorial of m plus n plus 1.
Okay, he doesn't see any obvious way he'd get that answer. Is it going to be easier to derive using Keltham's approach?
Keltham doesn't actually remember the exact proof. It's been a while, but he's pretty sure the introduction he used was the one his teachers used on him. So it's possibly the right introduction for getting the more complicated proof in the least painful way, once he starts trying to remember that. And in any case, Keltham hasn't yet been told he's allowed to assume that everyone in this class has a full intuition for derivatives and integrals yet. Keltham hasn't taught them a calculus class himself, and who knows what weird malfunctions exist in the Galarian way of teaching it. Why, it wouldn't shock him at this point if people are just being told to memorize formulas and not really taught to intuit how anything works. So he's just talking directly about the infinity of possible hypotheses between 0 and 1 and how to sum up priors times likelihoods and posterior predictions from those rather than using calculus to abstract over that. Abstracting over that only works to teach mathematical intuition if people already know what's being abstracted away. Keltham is in favor of people understanding things using calculus and continuous distributions, to be clear, so long as they can also understand the ideas in terms of a countably infinite collection of individual hypotheses, each with probability 1 divided by infinity. You don't want to start identifying either representation or methodology of analysis with the underlying idea. Which idea is just a meta-hypothesis where any fraction from 0 to 1 seems equally plausible on priors. Those get updated on observations of left and right that have different likelihoods for different propensity fractions. The allocation of posterior probability over fractions changes and gets normalized back to summing to 1. That changes the new predictions for left and right on successive rounds, having updated on all of the previous rounds. Keltham will now go up to the wall and spend a bit of time figuring out how to derive the rest of the rule of succession, which there's no simple or obvious way to prove using calculus known to anyone in this room anyways. Thankfully, they know what all the correct answers have to be, using much simpler combinatoric arguments about new balls ending up randomly ordered anywhere between the left boundary, all the left balls, the 0 ball, all the right balls, and the right boundary. Eventually, Keltham does succeed in deriving again, but this time proving it using dubious infinitary arguments instead of clear and simple combinatorics, so they can see what's happening with priors and posteriors, and likelihoods behind the scene. That indeed, if you start out thinking any fraction of left and right between 0 and 1 is equally plausible on priors, and you see experimental results going left on n occasions and going right on m occasions, the prediction for the next round is n plus 1 divided by n plus m plus 2 for left, and m plus 1 divided by n plus m plus 2 for right.
If you wish to support this AI reading and others like it, please visit patreon.com/AskWhoCastsAI. Any help is appreciated. And thank you to executive producer John Doe 7776059.